Let's get started, everyone. Welcome to session 3A. The first talk is Reed-Muller Codes Polarize by Emmanuel Abbe and Min Ye, and Min will give the talk.
Okay, thank you. So in this talk, we will talk about Reed-Muller codes, some new results on Reed-Muller codes for the purpose of data transmission. So let's just very quickly review the basic setup. We consider data transmission over a point-to-point communication channel. Okay, let's say we have a message represented by a binary sequence of length k. Then we, of course, encode this message by adding some redundancy, and we get a longer binary sequence of length m transmitted through the channel, and the channel added some noisy, and in the end, we use a decoding algorithm to recover the original message from the noisy code word. So here are a few parameters. The length of message k is called code dimension, and code length is n. Code rate is defined as a ratio between k and n. And finally, we want the decoding error probability to go to 0. So Shannon's seminal theorem in 1948 tells us that we can build reliable data transmission, namely we can make the decoding error probability decays to 0 if and only if the code rate is smaller than the channel capacity, which we denote as I of w. So Shannon's theorem was established in 1948. Of course, by today, we have already known several families of capacity achieving codes, like LDPC codes and polar codes, and maybe you have already heard of this. They both entered the 5G standards. So, but today we will talk about a more ancient code family called Reed-Muller codes. So recently, people found that there are quite a few similarities between polar codes and Reed-Muller codes. So this recent popularity of polar codes also brought back interest in the study of Reed-Muller codes for the purpose of data transmission. And this study has been going on for at least more than 60 years. Reed-Muller codes were proposed in 1954, but even till today, this major theoretical for Reed-Muller codes is still whether they achieve capacity or not. So this conjecture still remains open till today, except for some very special cases. And even the answers to these very special cases were obtained just like 3 or 4 years ago. So more precisely, in 2016, Kodecker and co-authors proved that Reed-Muller codes achieve capacity over erasure channels. So where let's say you transmit a sequence of bits through the channel, and the channel just independently erases every bit with a certain probability. So for such a channel, which is arguably the simplest channel that we can have, Kodecker and co-authors showed that Reed-Muller codes do achieve capacity over it. And there are also some other results showing that Reed-Muller codes with extreme arrays, namely arrays very close to 0 or very close to 1, also achieve capacity over erasure channel and binary symmetric channels. So in this talk, we make some advances on this conjecture over general communication channels, like binary symmetric channels or even binary input AWGN channels. And we show that actually Reed-Muller codes exhibit polarization behavior. And this is a necessary condition for Reed-Muller codes to achieve capacity. So the main tools that we use to prove that Reed-Muller codes have this polarization behavior is polarization theory developed in the context of polar codes. So let me first give you this background. We consider the most basic setup where we have a binary random variable with Bernoulli 1/2 distribution. We transmit it through some binary input channel with symmetric output. For example, you can just think of it as a binary symmetric channel where it flips each bit with independently with probability p. Okay, so for such a symmetric channel, we know that the channel capacity I of w is equal to the 1 minus the conditional entropy of x given y. And we consider, of course, multiple uses of this channel, and we do it in this way. Okay, so we have this we can think of this vector u1 to un as our information vector. They have ID Bernoulli 1/2 distribution. And let's say we have a binary, invertible binary matrix with size n by n. We denote it as Gn. We multiply the transpose of this column vector, u1 to un, with this matrix Gn, and we obtain our code word, x1 to xn, which is, of course, also ID Bernoulli 1/2. And then we transmit each xi through a channel W. We denote the output sequence of as y1 to yn. Okay, so now suppose that we want to use a successive decoder to decode the input sequence u1 to un from the output sequence y1 to yn. So by successive decoder, we mean that we decode this sequence u1 to un one by one, starting with u1, and then u2, and then u3, all the way down to un. Okay, and when we decode ui, we make use of not only all the channel outputs, but also the already decoded bits. Namely, we also make use of u1 to ui minus 1. So here we define this condition entropy hi. It is defined as the condition entropy of ui, given all the previous input bits u1 to ui minus 1, and all the channel outputs y1 to yn. Okay, so this condition entropy clearly it serves as a measure of the decoding error probability of the successive decoder for the ice bit, right? If this condition entropy is very close to 0, then we know that we can decode this bit successfully with very high probability. But if this condition entropy is bounded away from 0, for example, if it is very close to 1, then basically it says that all these previous bits and the channel outputs gives almost no information about ui. So here we say this matrix Gm polarizes if almost all the HIs, where I range from 1 to n, they are close to either 0 or 1. Okay? So now you might wonder, why do we need this concept of polarization? It is because of this theorem. It says that as long as we have a polarizing matrix Gn, it automatically gives us a capacity achieving code under the successive decoder. So this theorem is actually very simple, so let me just briefly tell you how to do it. So the code construction goes as follows. All we need to do is just to put all of our information in those UIs corresponding to HI close to 0. And we set all the other UIs to be some prefix value. Let's say set all of them to be 0, okay? So then, to show that this code achieves capacity, we only need to show two things. First, the decoding error probability goes to 0, but this comes directly from the code construction, because we only put information in those UIs that are more or less noiseless, right? Because these HIs are very close to 0. So the first thing is trivial. The second thing we need to show is that code rate is very close to I of W, but this, again, comes from the chain rule of conditional entropy, which is not to prove either, not difficult to prove either. Okay, so the whole theory of polar codes, just to give a concrete example of a polarizing matrix. So in polar codes, this Gn is defined as this Kronecker product of this 2x2 binary matrix, 1, 0, 1, 1. Okay, so how do you, I guess everyone here knows how to do Kronecker product. All you need to do is that if you multiply this A with this matrix, you just replace these 3 1s with A and keep 0 there. Okay. So here, let me give you a visual illustration of the matrix Gn. So we put a small black square at all the places where it is 1, and we leave it as blank for all the places where it is 0. Okay, so this is an illustration of G64, and this is illustration of G128. So you can see that how do we get G128 from G64? We just put this guy here in the upper left corner, lower left corner, and the lower right corner, and we leave this part, the upper right corner, as blank, which means that this is a 0 submatrix. Okay, so this is a polar code. Let me also very briefly explain why polar codes polarize. So here we start with this H. This is basically the conditional entropy of X given Y. This is basically 1 minus the capacity of the original channel. Okay, this is 1 minus capacity of original channel, and then you see we have a parameter M here. When M is equal to 1, we have 2 input bits. Therefore, we have H1 and H2. When M is equal to 2, we have 4 input bits. Therefore, we have H1, H2, H3, H4. So each time we increase M by 1, we will have 2 times more HIs. So it turns out that these HIs across different across consecutive values of M, they have a recursive structure described as follows. Okay, so for example, if you take M equal to 1, you have H1, 1 and H2, 1. Then the next 4 bits for M equal to 2 is obtained as, you just take 1 HI here and branch it out into 2 children. And in this way, you get 4 bits, and these are the 4 HIs for M equal to 2. And you always keep this branching out procedure. You will get, the HIs for arbitrary M. So this branching process has an important property. First, it has a Martingale property, means that the sum of its 2 children is equal to 2 times its parent node. And second, as long as the parent node is bounded away from 0 and 1, its children are also kicked away from itself. So this Martingale property tells us that this process will converge almost surely to a random variable. And the property that as long as this HI is bounded away from 0 and 1, its children will kick it away from itself. It says that only 0 and 1 are the stable points of this Martingale process. Therefore, in the end, the stable distribution of the final random variable are only supported on 2 points. They are 0 and 1. That's why this matrix GM polarize. So now we move on to Reed-Muller codes. It turns out that Reed-Muller codes are just the matrix for Reed-Muller codes, matrix Rn for Reed-Muller codes, is just a row permutation of Gn. It is done, the row permutation is done in such a way that the rows of Rn always have increasing Hamming weight. Okay, so the first row has weight 1, and the last row has weight n. So these two are still square matrices. So for the data transmission, we of course only use some rows of these 2 square matrices. So for polar codes, as we already said, we choose UI with those HIs more or less 0, right? So this takes out some rows from this matrix. In contrast, for Reed-Muller codes, we only use UIs in the bottom part of its vector. More precisely, we take some threshold I0, and then we set all the UI to be 0 for all I less than I0. And we put all of our information in those UIs where I is larger than or equal to I0. Okay? So basically, we only use the generator matrix of Reed-Muller codes is just some bottom part of this square matrix. Okay, so now we have all the background, and we are ready to state our main result. The first main result is that we show the polarization of Reed-Muller codes. More precisely, we show the polarization of this matrix Rn. Namely, all the HIs are close to either 0 or 1 for this bottom graph. Okay, for this case. And as we said, whenever we have a polarizing matrix, in this case it is Rn, it automatically gives us a capacity achieving code. Okay, all we need to do is to choose all those HIs that are close to 0 for this matrix Rn. And we call such a code the twin Reed-Muller codes. And we can show that, in fact, Reed-Muller codes achieve capacity if and only if they are almost the same as twin Reed-Muller codes. So here, almost the same means that their generator matrices differ by at most a vanishing fraction of rows. And finally, we also prove a partial order on these conditional entropies HIs. So at the beginning, I talked about the capacity achieving conjecture for Reed-Muller codes. So now we have this main result talking about the polarization of Reed-Muller codes. Now you might wonder what is the relation between our main results and the conjecture. So in fact, you can easily show that polarization of Reed-Muller codes itself is a necessary condition for Reed-Muller codes to achieve capacity. On the other hand, polarization together with a strong ordering on the HIs will become a sufficient condition for Reed-Muller codes to achieve capacity. So here, by strong order, I mean if you can show that, for example, all the HIs are monotonically decreasing, then basically you know that all the HIs are either 0 and 1, and then they are monotonically decreasing, then you know that the bottom part are all 0. So you know that you should indeed put the information in the bottom part, and that's exactly what Reed-Muller codes do. Okay, so this is a sufficient condition. So our results is in between. So we indeed proved the polarization, but we didn't manage to prove the strong ordering. We proved something weaker. We only proved a part of this strong ordering. So that's what we get. And here I also want to say a few words about the proof idea. So as we said in the polar codes, there is a tree structure. For example, if originally you have 4 HIs, and in the next level you will get 8 HIs, and this 8 HIs is obtained such that one of the children is smaller than the original point, and one of the children is larger than the original point. So there is always a gap, okay, between these two children. What we can show for Reed-Muller codes is that, in fact, the Reed-Muller transform will only make this gap larger. It will only make the smaller one even smaller, and the larger one even larger, right? So as we said, for polar codes, as long as this parent is bounded away from 0 to 1, the gap between its children is large. And for Reed-Muller codes, we can show the gap is even larger. But unfortunately, for Reed-Muller codes, we do not have that Martingale property, right? For polar codes, we know that the sum of these two children is equal to 2 times its parents. But for Reed-Muller codes, we lose this. So there are some technical difficulties we need to get around. And of course, I don't have time to talk about it here. But this figure gives you kind of some intuition why Reed-Muller codes should also polarize, because the gap becomes larger and larger. Okay, so now I want to summarize this talk. Our work, in fact, is, to our knowledge, is the first attempt to analyze Reed-Muller codes using the theory from polar codes. And we obtained some partial success because, of course, we get something between necessary and sufficient condition for Reed-Muller codes to achieve capacity. So here are 3 future directions. The most obvious one is try to close the conjecture. The second one is to try to get a better quantification of the gap to capacity. Maybe I don't have time to explain that. The third one is maybe try to extend this result over to the larger finite fields. So in our work, we only consider this result for a binary field. Okay, so that's all. Thank you.
Questions?
Can you say what is it about Reed-Muller that you said that you don't obtain Martingale for it? So what is it in there that you actually really use that you get this?
You mean here?
Yes. You don't have the Martingale there, so what do you have?
So basically, we divide these HIs into many chains. Each into many, let's say, subsets, okay? So each subset of HIs, each subset contains m plus 1 HIs. And we show that for each of such subset, these HIs, they have a polarizing behavior, meaning that only a constant fraction of them will be bounded away from 0 and 1. And then we do a kind of an averaging argument over all these subsets. But I guess in order to explain that, we need definitely much more notation. Even the notation is not fully introduced here to explain that. But
so do your techniques extend to transitive codes as well, like the BEC case, or it's just Reed-Muller?
I think it's just the Reed-Muller, because Reed-Muller codes have these recursive structures. It heavily relies on the recursive structure of Reed-Muller codes. Actually doesn't have, it makes use of some symmetric property, but doesn't rely very heavily on that.
Last question, yeah.
Can you describe what the weak order means? What do you mean?
I'm sorry?
So there was a part where you said that you show it polarizes with weak order or something. What does that mean? There was a table where you had strong order would be sufficient.
Oh, I see.
What does the weak order mean?
For example, the strong order means that, roughly speaking, the HIs are decreasing. And this weak order is just we prove that some pair of HIs have this decreasing property, not for all pairs. That's roughly speaking, it's that.
Okay, we need to get to the next speaker, so let's thank the speaker again.